The first thing you noticed was the heat. Not the Ohio summer heat, though that was bad enough. August in Cincinnati could press 95 degrees against your skin like a wet hand. No, this was different. This was the heat coming off an engine that had just been run for 6 minutes on a dynamometer stand at the Wright Aeronautical plant in Lockland, Ohio, and had to be shut down because the rear row of cylinders was glowing cherry red. Not metaphorically, literally cherry red, the color of a horseshoe fresh from the forge, visible in the dim light of the test cell, even through the haze of burned oil smoke that hung in the air like a warning. The date was sometime in the late summer of 1942. The engineer standing closest to the test cell door, close enough to feel the radiant heat on his forearms, was watching the temperature gauges wind down and doing arithmetic in his head that no one in the room wanted to hear. The Wright R-3350 Duplex-Cyclone, the engine that was supposed to power the most important bomber in American history, had just demonstrated for the 14th or 15th time that it could not cool itself. The rear 9 cylinders, tucked behind the front 9 in a double-row radial configuration, were starving for air. They ran hot, they burned oil, they cracked exhaust valves, and when they failed, not if, when, they sprayed magnesium and aluminum fragments into the nacelle where they met fuel vapor and became fire. The B-29 Superfortress existed on paper. Boeing had the airframe. The Army Air Forces had the contract. General Hap Arnold had staked his career and arguably the outcome of the Pacific War on a bomber that could fly higher than 30,000 feet, carry 10,000 pounds of bombs, and reach Tokyo from bases that hadn't been captured yet. Everything about the airplane was radical. Pressurized crew compartments, remote-controlled gun turrets, a central fire control computer, tricycle landing gear. It was, by any honest measure, the most technologically ambitious aircraft program of the Second World War. And it had no engine. That is not quite true, and the distinction matters. It had an engine on paper. It had an engine on the dynamometer. It had an engine that could produce 2,200 horsepower for brief, spectacular intervals before something inside it broke, melted, seized, or caught fire. What it did not have was an engine that could do this reliably for 500 hours, the minimum the Army demanded before it would accept a power plant for combat service. In mid-1942, the R-3350 could barely manage 50. The gap between those two numbers, 50 hours and 500, was not an engineering inconvenience. It was a chasm into which men, money, time, and eventually lives would be poured in quantities that make the Manhattan Project look, by comparison, like a tidy operation. The atomic bomb program cost roughly $2 billion. The B-29 program cost $3 billion. And the single largest reason for that cost, the single most persistent source of delay, disaster, and death, was the engine that sat 2 to a wing on every Superfortress that rolled off the line in Wichita, Omaha, Marietta, and Renton. This is the story of the Wright R-3350, the engine that was asked to do something no aircraft engine had ever done, and that kept killing people while it learned how. The problem was thermodynamics, and thermodynamics does not negotiate. An 18-cylinder radial engine producing over 2,000 horsepower generates heat in quantities that are difficult to grasp without analogy. Each cylinder of the R-3350 displaced approximately 186 cubic inches, roughly the size of a 3-liter soda bottle, and roughly the same displacement as the entire engine in a modern compact car. There were 18 of them, arranged in 2 rows of 9, bolted to a forged crankcase that weighed as much as a grown man. Total displacement? 3,347 cubic inches, or nearly 55 liters. At takeoff power, each cylinder was firing its spark plugs, compressing fuel-air mixture, and expelling superheated exhaust gases more than 15 times per second. The total thermal energy released by this process, if captured and converted perfectly, could have heated a small apartment building. But it could not be captured perfectly. That was the problem. In a single-row radial, the kind Wright had been building successfully since the late 1920s, each cylinder sat exposed to the oncoming airstream. Cooling fins machined into the cylinder heads and barrels transferred heat from the metal to the passing air, and the air carried it away. Simple. Effective. The Wright R-1820 Cyclone, a 9-cylinder single-row radial, was one of the most trusted engines of the 1930s. It powered the B-29 Flying Fortress. It ran cool, ran long, and almost never caught fire. The R-3350 was not a single-row radial. It was a double-row, 2 banks of 9 cylinders sharing a single crankshaft. The rear row staggered behind the front. This arrangement was necessary to achieve the displacement and power the B-29 required without making the engine's frontal area so large that it created unacceptable drag. A single row of 18 cylinders would have been absurdly wide. The cowling alone would have been the diameter of a small room. So the cylinders were stacked, front and back, in a compact package roughly 4 feet across. The front row ran fine. It sat directly in the airstream, just as God and the laws of convective heat transfer intended. The rear row did not. It sat in the aerodynamic shadow of the front row, receiving only turbulent, preheated air that had already passed over 9 hot cylinders before reaching the 9 behind them. The temperature differential was staggering. On a tropical day at full power, the exact conditions the B-29 would encounter on every mission over Japan, the rear cylinders could run 150 degrees Fahrenheit hotter than the front. Exhaust valves warped, valve guides seized, cylinder heads cracked, oil carbonized in the valve train and turned to abrasive paste. And when a cylinder failed, the magnesium alloy crankcase, chosen for its light weight, became kindling. Wright Aeronautical was not a company accustomed to failure. Founded in 1919 from the remains of the Wright-Martin Aircraft Corporation, itself a distant corporate descendant of the company Orville and Wilbur Wright had built, it had spent 2 decades establishing itself as one of America's 2 dominant aircraft engine manufacturers, the other being Pratt & Whitney. The rivalry between them was fierce, personal, and occasionally petty. Wright had Cincinnati. Pratt had Hartford. Wright had the Cyclone. Pratt had the Wasp. Each company believed, with the conviction of evangelical religion, that its design philosophy was superior. Wright's philosophy was the radial air-cooled engine, and by the mid-1930s, the company was already looking ahead to the next generation. The R-2600 Twin Cyclone, a 14-cylinder double-row radial producing around 1,700 horsepower, entered development in 1935 and would go on to power the B-25 Mitchell, the TBF Avenger, and the A-20 Havoc, among others. It was a good engine. But the Army Air Corps wanted more. More power, more altitude, more range. The specification that would become the B-29 demanded an engine producing at least 2,000 horsepower, preferably more, with the reliability to sustain it at altitudes above 25,000 feet for missions lasting 16 hours. No such engine existed anywhere in the world in 1938, when Wright began serious design work on the R-3350. The man most responsible for the engine's initial design was a Wright engineer named George J. Meade, though Meade's role in the company's engineering hierarchy makes precise attribution difficult. Wright's engineering culture was institutional rather than heroic. Decisions were made by committees, validated by test, and recorded in reports that named departments rather than individuals. This was not the kind of shop where a lone genius sketched a revolution on a napkin. It was the kind of shop where 40 men in short-sleeved shirts argued about cooling fin pitch for 3 weeks and then tested both options. What they designed, over the course of roughly 3 years, was an engine of breathtaking ambition and marginal practicality. The R-3350 was, on paper, everything the Army wanted. 18 cylinders, a 2-speed supercharger, forged steel connecting rods, a propeller reduction gear that could handle the torque of 2,200 horses without stripping its teeth. Each cylinder had 2 intake valves and 2 exhaust valves, a 4-valve head that improved breathing and should have improved cooling. The crankshaft was a masterpiece of metallurgy, a single forging that converted 18 separate combustion events per revolution into smooth rotational power. The engine first ran on a test stand in 1941. It made power. It also made trouble. Then came Pearl Harbor, and trouble became catastrophe. The Japanese attack in December 1941 did not create the need for the B-29. Boeing had been working on the design since 1939, but it transformed the program from an ambitious development project into an existential priority. The Pacific Ocean was vast. The distances involved were unlike anything the European theater demanded. From any base the United States could reasonably hope to capture or build, Tokyo was more than 1,500 miles away. No existing American bomber could make that trip with a useful bomb load and return. The B-17 could not do it. The B-24 could not do it. The B-29 was the only airplane in development that even theoretically could. General Henry Hap Arnold understood this with a clarity that bordered on obsession. Arnold was the commanding general of the Army Air Forces, and he believed, with a faith that was religious in intensity, that strategic bombing could win the war against Japan without the catastrophic ground invasion that military planners were already dreading. But strategic bombing required bombers, and bombers required engines, and the engine required for this particular bomber did not yet work. Arnold's response was to do something that violated every principle of orderly military procurement. In September 1942, before the R-3350 had passed its qualification tests, before it could run for 500 hours without failure, he ordered the B-29 into mass production. Not into extended testing, not into limited pre-production, into full-scale manufacturing, at a rate that would eventually demand thousands of engines per month. He was ordering the Army Air Forces to build an airplane around an engine that did not yet function reliably, on the assumption that it would be fixed by the time the airplanes were ready to fight. This decision has been called brilliant and insane in roughly equal measure by historians. Arnold himself reportedly described it as a $3 billion gamble. What it meant in practical terms was that Wright Aeronautical had to simultaneously do two things that are almost impossible to do at the same time: fix a fundamentally flawed engine and mass-produce it by the thousands. The production numbers demanded were staggering. The Army wanted nearly 4,000 B-29s. Each required 4 R-3350 engines plus spares. Accounting for attrition, training, and overhaul, the total engine requirement was somewhere north of 20,000. Wright's existing plant in Paterson, New Jersey, could not absorb this. A new plant at Lockland, later called the Evendale facility, was already under construction. Additional production was subcontracted to the Dodge division of Chrysler, which would build the engine in a massive new factory in Chicago. Automobile companies building aircraft engines. It was a pattern repeated across American industry during the war, and it was never as simple as it sounded. A Chrysler engineer accustomed to casting engine blocks for sedans, parts that were heavy, robust, and tolerant of imprecision, now had to produce aircraft cylinder heads machined to tolerances of 1/1000th of an inch, from aluminum alloys he had never worked with, using processes his shop foreman had never seen. The learning curve was vertical and expensive. The fixes came slowly, painfully, and accompanied by funerals. The core cooling problem, those starving rear cylinders, was attacked from multiple angles. Wright redesigned the cylinder baffling, the sheet metal guides that directed cooling air around each cylinder. The original baffles had been designed using wind tunnel data and theoretical airflow calculations. They were wrong. The turbulence behind the front cylinder row was worse than the models predicted, and the baffles did not force enough air over the rear cylinder fins. New baffles were designed, tested, redesigned, tested again. Each iteration required new tooling, new manufacturing procedures, and weeks of dynamometer testing. The exhaust valves were another nightmare. Made from a nickel alloy called stellite, they were supposed to withstand the temperatures and corrosive environment inside the combustion chamber. They didn't, at least not at the temperatures the rear cylinders were reaching. The valves warped, losing their seal against the valve seat. Hot exhaust gases blew past the damaged seal, eroding the valve further in a vicious feedback loop that ended with valve failure, cylinder failure, and often fire. Wright experimented with sodium-cooled exhaust valves, hollow valves partially filled with metallic sodium which melted at operating temperature and sloshed back and forth, transferring heat from the valve head to the stem where it could be conducted into the cylinder head and carried away by cooling air. The concept worked. The execution was tricky. If the valve cracked, molten sodium meant moisture, and the chemistry was unkind. Propeller reduction gear failures added another dimension of anxiety. The gear train that reduced crankshaft speed to propeller speed, necessary because a propeller blade tip moving faster than the speed of sound loses efficiency catastrophically, was transmitting more torque than any previous American aircraft engine had produced. Gear teeth chipped, bearings failed. Oil starvation at altitude, where the lubricant thinned in the cold, caused gears to run dry and weld themselves together in a shower of metal fragments that sounded, to the flight engineers sitting behind the cockpit, like a bag of hammers thrown into a washing machine. The human cost of these failures was not abstract. On February 18, 1943, a B-29 prototype, the second XB-29 built, serial number 41003, took off from Boeing Field in Seattle for a routine test flight. The legendary test pilot Eddie Allen was at the controls. Allen was one of the most experienced test pilots in America, a man whose calm under pressure was the stuff of industry legend. 11 minutes after takeoff, the number 1 engine caught fire. Allen reported the fire and turned back toward Boeing Field. The fire spread to the wing. The airplane crashed into the Fry meatpacking plant near the airfield, killing all 11 crew members aboard the aircraft and roughly 20 workers in the building below. The investigation pointed to the engine, specifically to an engine fire that exceeded the capacity of the nacelle fire extinguishing system and burned through the wing spar. The tragedy was compounded by the fact that this was not a surprise. Engine fires had been reported repeatedly during ground testing and early flight testing. The R-3350 was known within the engineering community as a fire hazard. Allen's death and the deaths of the men with him were, in the coldest possible analysis, predictable. Senator Harry Truman's War Investigating Committee, the same committee that had made Truman a national figure by exposing waste and incompetence in defense production, launched an inquiry. Wright Aeronautical was scrutinized, Boeing was scrutinized, the Army Air Forces was scrutinized. The fundamental question was blunt. Why was a $3 billion airplane program being built around an engine that kept catching fire? The answer, which satisfied no one, was that there was no alternative. No other American engine of sufficient power existed. Pratt & Whitney's R-4360 Wasp Major, a 28-cylinder 4-row radio that would eventually produce over 3,500 horsepower, was even further from readiness. Going back to a smaller engine meant a smaller airplane, shorter range, lower altitude, fewer bombs, and the loss of everything the B-29 was supposed to accomplish. Arnold's gamble was not a gamble because he liked risk. It was a gamble because the alternative was no gamble at all, just surrender of the strategic bombing mission against Japan. So they kept building the engine, and they kept fixing it, and men kept dying in the process. By mid-1943, the factory floor at Lockland consumed a person whole. The main assembly building stretched more than a quarter mile in one direction, and the noise inside it was a physical thing, not just loud, but layered, a geological strata of sound. The bottom layer was the constant industrial hum of ventilation, conveyor belts, and fluorescent lighting. Above that, the staccato percussion of rivet guns, the whine of milling machines cutting aluminum, the sharp crack of torque wrenches. And above it all, From the test cells at the far end of the building, the unmistakable full-throated bellow of an R-3350 at takeoff power, a sound that vibrated in the chest cavity and made conversation impossible within 200 feet. The workers who built these engines were, by 1943, increasingly women. The narrative of Rosie the Riveter is well known, perhaps too well known. It has been smoothed into a feel-good story of empowerment when the reality was more complicated and more interesting. Many of the women at Lockland had worked before the war in textile mills, laundries, or domestic service. Some had never held a tool heavier than a kitchen knife. They were trained in weeks to perform operations that peacetime apprenticeships would have stretched across years. A woman assembling exhaust valve guides, a task requiring the insertion of a precise metallic sleeve into a cylinder head bore using a hydraulic press and a tolerance gauge, was performing work that directly determined whether a cylinder would overheat and fail over Kobe or Nagoya. The quality control pressure was enormous. Every engine was tested before delivery. Every engine that failed its test, and many did, was torn down, inspected, repaired, and tested again. Rejected engines piled up in a holding area that workers called the graveyard, rows of disassembled power plants on wooden pallets, their crankcase halves spread open like mechanical autopsies. The defect rate in 1943 was alarming. Wright's own internal reports documented problems with porosity in crankcase castings, improperly heat-treated connecting rods, and cylinder barrels with machining marks that acted as stress risers, tiny imperfections that, under the cyclical loading of thousands of combustion events per minute, would nucleate cracks and propagate failures. At the Dodge Chicago plant, the problems were different but no less severe. Chrysler's engineers were supremely competent at mass production. They knew flow, they knew tooling, they knew how to move material through a factory with ruthless efficiency. What they did not know was aircraft engine metallurgy. The alloys used in the R-3350, forged aluminum cylinder heads, nitrided steel cylinder barrels, silver-lead bearings, behaved differently from the cast iron and mild steel that Detroit knew intimately. Chrysler had to learn on the job, and the tuition was paid in scrapped parts and failed engines. Production ramped up regardless. By late 1943, Wright and Dodge combined were producing hundreds of R-3350s per month. By early 1944, the number exceeded 1,000. Each engine weighed approximately 2,670 pounds dry, over 1.25 tons of precision-machined metal that had to function flawlessly in conditions ranging from tropical sea-level heat to the -60-degree cold of the stratosphere. The engine went to war before it was ready, because the war would not wait. The first B-29 combat mission launched on June 5, 1944, the day before D-Day, though the coincidence was unintentional. 98 Superfortresses of the 58th Bombardment Wing took off from bases around Kharagpur, India, bound for the Makasan Railroad Yards in Bangkok, Thailand. The mission was a logistical compromise. Bangkok was within range of India, while Japan was not, and its purpose was as much operational training as strategic bombing. The results were not encouraging. Of the 98 aircraft that launched, only 77 reached the target area. 14 aborted with mechanical problems, the majority of them engine-related. 5 aircraft were lost, none to enemy action, all to mechanical failures or operational accidents. The bomb damage to the railroad yards was negligible. The R-3350's behavior in the field confirmed what the test engineers had feared. Engines overheated on the long taxi to the runway, a process that could take 30 or 40 minutes on the crowded Indian airfields. Cylinder head temperatures climbed past redline during the extended high-power takeoff roll, and pilots who throttled back to save their engines risked not clearing the obstacles at the end of the strip. Once airborne, engines that had been abused during takeoff would occasionally seize, swallow a valve, or simply catch fire with a suddenness that left the flight engineer no time to react. Sergeant Henry "Red" Irwin's story would come later, over Koriyama, Japan in April 1945, but it captures something essential about what it meant to fly behind these engines. Irwin was a radio operator, not a mechanic, but every man on a B-29 crew understood the engines intimately because their lives depended on them. The pre-flight ritual included a careful inspection of each nacelle for oil leaks, a check of the cowl flap actuators, and a silent prayer, spoken or unspoken, that today would not be the day the No. 3 engine decided to eat itself. Staff Sergeant Jack Spratt, a flight engineer with the 462nd Bombardment Group, kept an informal log of engine failures during the group's first 6 months of operations from India. His list, preserved in a memoir published decades later, is a catalog of mechanical mayhem. Cracked cylinders, thrown rods, burned pistons, failed magnetos, oil leaks that emptied a 35-gallon tank in 20 minutes, propeller governors that ran away and sent engine RPM screaming past redline before the engineer could reach the feathering button. Spratt noted that his airplane went through 11 engines in 4 months. Not the same engine repaired 11 times. 11 different engines, removed and replaced because they had failed or were about to. The fire problem was the worst. The R-3350's exhaust system ran close to the nacelle structure, and any engine failure that involved a cracked cylinder or a broken exhaust stack could spray burning oil and raw fuel into a space full of magnesium and aluminum. The nacelle fire extinguisher system, a bottle of carbon dioxide that could be discharged into the engine compartment with the pull of a handle, was frequently inadequate. A fire that was not extinguished within seconds could burn through the main wing spar in less than 2 minutes. When the spar failed, the wing folded. There was no surviving that. The crews developed their own countermeasures, born of desperation and ingenuity. Some flight engineers ran the cowl flaps wider than the manual specified, accepting the drag penalty in exchange for lower cylinder head temperatures. Others nursed the throttles with a finesse that would have impressed a concert pianist, making tiny adjustments constantly to keep temperatures in the narrow band between too cool for efficiency and too hot for survival. The best flight engineers could hear an engine change pitch before the gauges showed anything, a skill that was not taught so much as earned through survival. What the Japanese had on the other side of this equation was almost nothing. Japan's aero engine industry in 1944 was producing capable engines, the Nakajima Homare, the Mitsubishi Kasei, but nothing in the class of the R-3350. The most powerful Japanese production engine, the Nakajima NK9 Homare, produced roughly 1,800 horsepower from an 18-cylinder double-row radial that suffered, ironically, from many of the same overheating problems as the R-3350, but without the industrial infrastructure to fix them. Japan's metallurgical base was shrinking under the pressure of submarine blockade and strategic bombing. High-quality alloy steels, the kind needed for exhaust valves and crankshafts, were becoming scarce. Cylinder production was plagued by porosity defects that Japanese quality control, less systematic than its American counterpart, sometimes failed to catch. The asymmetry was not just in the engines, it was in the capacity to produce them, fix them, and improve them while a war was being fought. The United States could afford, in the material and moral sense, to send an imperfect engine into combat because it had the industrial depth to keep modifying it until it worked. Each month's production incorporated the fixes learned from the previous month's failures. New baffle designs, improved exhaust valves, better oil formulations, revised maintenance procedures. The R-3350 of January 1945 was a substantially different engine from the R-3350 of January 1944, even though the type designation was the same. Japan could not do this. Its engine factories were being bombed by B-29s running those same troubled engines, and its supply chains were being severed by submarine warfare. An engine defect discovered in the field could not be corrected at the factory because the factory might no longer exist or might lack the raw materials to implement the fix. The Japanese pilot flying a Kawanishi N1K Shiden with a problematic Homare engine had no expectation that next month's engine would be better. The American pilot flying a B-29 with a problematic R-3350 could at least hope. Germany, for its part, had taken an entirely different path. The Luftwaffe's heavy bomber program had been effectively abandoned by 1942, a strategic decision that reflected Germany's preference for tactical air power and its inability to sustain multiple enormously expensive development programs simultaneously. Germany had no equivalent of the B-29 and no equivalent of the R-3350. The closest comparison, the BMW 801, a 14-cylinder double-row radial producing around 1,700 horsepower, was a fine engine, but it was designed for fighters and medium bombers, not for the kind of high-altitude, long-range strategic mission that defined the Superfortress. The American willingness to tolerate an imperfect engine, to mass-produce it while still debugging it, to accept casualties in the development process and press forward, this was not, strictly speaking, an engineering triumph. It was an industrial and organizational philosophy, a bet that volume and iteration would solve problems that perfection before production never could. Whether it was admirable or reckless depends on where you stood. If you stood in a factory in Lachlan, it felt like progress. If you stood in the cockpit of a B-29 over Osaka watching your No. 2 engine trailing black smoke, it felt like something else. The engine grew up. That is perhaps the most surprising part of the story. By mid-1945, the R-3350 was no longer the catastrophe it had been 18 months earlier. The improvements were cumulative and real. Redesigned cylinder baffles improved rear-row cooling by roughly 40 degrees Fahrenheit. Not enough to eliminate the problem, but enough to push it below the threshold of routine failure. New exhaust valve materials and sodium cooling reduced valve failures to manageable levels. Improved oil formulations resisted carbonization at high temperatures. Revised propeller reduction gears, manufactured to tighter tolerances and better heat-treated, stopped eating themselves. The fire problem was never fully solved during the war, but it was mitigated. Better nacelle drainage, improved firewall seals, and larger fire extinguisher bottles gave crews a fighting chance against engine fires that would have been fatal a year earlier. The XX Bomber Command, operating from China and India, had suffered engine-related losses that were, per sortie, worse than combat losses. The XXI Bomber Command, operating from the Marianas beginning in late 1944, saw those rates decline steadily as improved engines and better maintenance procedures reached the field. When General Curtis LeMay made his controversial decision in March 1945 to switch from high-altitude daylight precision bombing to low-altitude nighttime incendiary raids, one of the underappreciated consequences was a dramatic reduction in engine stress. Flying at 5,000 to 9,000 feet instead of 25,000 to 30,000 feet meant lower manifold pressures, lower cylinder head temperatures, and less strain on the supercharger. The engines lasted longer, the fires decreased. The R-3350 at low altitude was, if not reliable, then at least survivable. After the war ended, the engine found a second career. The post-war era of commercial aviation, the period between 1945 and the coming of the jets, was the age of the large piston engine, and the R-3350 was its monarch. Significantly redesigned and fitted with turbo-compound power recovery turbines, exhaust-driven turbines that fed power back into the crankshaft, extracting energy that would otherwise have been wasted as heat, the R-3350 became the engine of choice for the Lockheed Constellation and the Douglas DC-7, two of the most important airliners of the 1950s. In this application, properly maintained by airline mechanics who were not being shot at, running at cruise power rather than emergency war power, the engine was finally what it had always been designed to be: powerful, efficient, and reasonably reliable. The turbo-compound version produced up to 3,700 horsepower, nearly 70% more than the wartime version, and its specific fuel consumption was among the lowest of any piston engine ever built. TWA, Pan American, Eastern, and others flew millions of passenger miles behind R-3350s without the kind of drama that had characterized their wartime service. The engine that killed Eddie Allen carried tourists to Paris. Wright Aeronautical itself did not survive the transition as gracefully. Merged with Curtiss Aeroplane and Motor Company during the war to form Curtiss-Wright, the combined company found its core business evaporating as jet engines replaced pistons in both military and commercial aviation. Curtiss-Wright pivoted to other products, nuclear instrumentation, metal treatment processes, industrial valves, and exists today as a diversified industrial company based in Davidson, North Carolina, with annual revenues north of $2 billion. It does not make aircraft engines. The last R-3350 rolled off the production line sometime in the 1950s, and the factories where they were built have been repurposed or demolished. There is a photograph, taken sometime in 1944, that hangs in the collections of the National Air and Space Museum. It shows a woman, her name is not recorded, standing on a raised platform at the Wright Lockland plant, leaning over the exposed crankcase of an R-3350 with a torque wrench in her right hand. She is wearing coveralls, safety glasses, and a bandana over her hair. Her left hand is braced against the engine for balance. The engine is enormous beside her, the cylinder heads rising to her shoulders, the propeller shaft pointed toward the camera like a cannon barrel. She is installing connecting rod bolts. Each bolt must be torqued to a precise specification. Too loose, and the rod bearing will shift under load. Too tight, and the bolt will stretch and fail in fatigue. The tolerance band is measured in foot-pounds, a unit of rotational force that she has learned to feel through the handle of the wrench in her palm. She has done this hundreds of times. She will do it hundreds more. Each bolt she torques correctly is a tiny, incremental contribution to the possibility that an engine will hold together over Tokyo, that a bomber will return to Tinian, that a crew of 11 men will walk away from their airplane and eat dinner and write letters home. She does not know their names. She will never know their names. The separation between the factory and the battlefield was total and deliberate. The women and men who built these engines had no contact with the crews who depended on them, no feedback loop of gratitude or blame. The engine was the intermediary, the mechanical proxy through which one American's labor became another American's survival or death. The R-3350 was never a great engine in the way the Rolls-Royce Merlin was great, or the Pratt & Whitney R-2800 was great. Engines that arrived in the world more or less ready to do their jobs, and did them with a consistency that inspired genuine affection. The R-3350 was a difficult engine, a troubled engine, an engine that demanded more of its builders and its operators than any reasonable person would have asked. It caught fire, it killed test pilots, it failed at the worst possible moments. It was rushed into production before it was ready, mass-produced by workers who had never built anything like it, and sent to war in an airplane that could not afford to fly without it. But it flew. It improved. It carried the war to Tokyo when nothing else in the American arsenal could reach that far. And the people who built it, the engineers in Cincinnati, the machinists in Chicago, the women at Lockland with their torque wrenches and their safety glasses, did not have the luxury of waiting until the engine was perfect. They built what they could as fast as they could, and they fixed it while it fought. The R-3350 did not betray its crews. It struggled alongside them. And in the end, later than anyone wanted, at a cost higher than anyone planned, it did what it was built to do.